Looking back then at the idea we looked at for electromagnets, that is to say, if a current flows through a wire, there's a magnetic field around the wire. And we're able to predict the direction of the field around the wire using the right-hand grip rule. If you hold the wire with your thumb pointing in the direction of the current, this is your right hand, then your fingers will show the direction of the field lines running from your thumb around to the tip. That's the direction of the field lines. So if you take that wire and you put it between the poles of a magnet in another magnetic field, then that wire experiences a force, and this is why. You've got two magnetic fields, and where the field lines add together from the wire and the magnet, you get a stronger field, in this case above the wire. Below the wire, the fields are going in opposite directions, so you get a weaker field, and so the wire moves in the direction of the weaker field. Towards the weaker field is what I mean. So you have a force on the wire. Now, if you increase the current through the wire, you strengthen the magnetic field around the wire like you did with the coil for an electromagnet. So a larger current will make a stronger magnetic field and therefore a larger force on the wire. If you use stronger magnets, note stronger, not bigger, you need more field lines per square centimeter, not more square centimeters of magnet. So a stronger magnet, not a bigger magnet, or using more turns of wire, making this from a single wire into a coil of wire by having turns in the coil. So note the animation said larger field, that's wrong, it is a stronger field that you need there. So those are the ways to make the force on the wire greater. If you reverse the direction of the current, you reverse the direction of the field around the wire, and so you reverse the direction of the force on the wire in the magnetic field. If you reversed both, of course, the reversing of one counteracts the effect of reversing the other, and there is no change. So, how do you predict the direction of the force? Well, this is Fleming's left-hand rule. You need to be able to quote the rule, if you state what the rule is in words. You also have to be able to use the rule. So pay close attention to this and make sure you get it. You place the first finger, second finger and thumb of your left hand at right angles to each other. The first finger is a direction of the field from north to south. The second finger is a direction of the current going from positive to negative. And the thumb then shows you the direction of the force on the wire. So all of that pulls together into the motor. Here we have a coil of wire made up of several turns. Each of those turns will experience the same force. So if you've got two turns, you've got twice as much force then on this side of the coil. 10 turns, 10 times as much force as if you had just a single piece of wire. So what we need the motor to do, of course, is to rotate the coil. We want to convert electrical energy into rotational kinetic energy. So when this side here, which is the side the current is coming out of the coil along, when this side lands over here, if the current is still coming out along that, now the force will be reversed. So the force is down on this side because the current is going in along this side. When this side lands over here, if the current is still coming out along that side, the force will not be down, it'll be up. So what your coil would do would be to oscillate. That's no good. We want it to rotate. So we have to make sure that when this side lands over here, the current is still coming in past the North Pole. That's where your commutator comes in. These two semicircles of brass attached to the ends of the coil rotate with the coil so that the current is always flowing in past the North Pole and out past the South Pole. So the coil always experiences a force down on whatever side is over here and up on whatever side is over here, so the coil always rotates anti-clockwise. You have graphite brushes, graphite because it is a conductor being pushed in on springs against the commutator to make a nice solid electrical contact. And that's basically your motor. Magnetic field, coil of wire, commutator. This is a DC motor. We will look at an AC motor later on. So end on then, this is what you would see. Current always flows in from the left and then in along the coil of wire past the North Pole. It always flows out on the right, which means it's flowing out past the South Pole. And so because the current always follows the in past the north, out past the south route, the coil always turns in the same direction, in this case anti-clockwise. If you increase the current through the coil, you will increase the force, and so you'll increase the power of the motor. It will turn faster. Likewise, stronger magnetic field, more turns of wire in the coil, but clearly if you want the motor to turn faster or slower in a piece of equipment, what you're going to do is change the current. Notice it is always the current we talk about. We will change the current by changing the PD across the coil, but we are changing the current. It is the current that's important. Now, another device that works on exactly the same principle is the loudspeaker. But this time we don't want the loudspeaker to rotate, we want it to vibrate in and out. So what we have is an alternating current flowing into the coil. As the current rises in value, the force on the coil gets bigger. As the current falls, the force on the coil gets smaller. As the current changes direction, the force on the coil changes direction, and so the coil vibrates. Now, of course, the current is coming in, it's going maybe in past this North Pole. So then if we didn't have another one down here, if we just had north and south, it would be going in past the north, out past the south, which would mean that you'd have a force in one direction on the top of the coil, in the other direction on the bottom of the coil, and the coil would not vibrate. So we have the top of the coil in one field and the bottom of the coil where the current has changed direction. It's coming in over the top and out along the bottom. So the current has changed direction. We also change the direction of the field, so it goes north-south, coming from top to bottom, then it goes south-north. So we have reversed both the direction of the current and the direction of the field down here, which means that if the force on the top is that way, the force on the bottom is also that way. So this is why we have this tripolar field, 3 poles rather than 2. So we have an alternating potential difference across the coil, giving us an alternating current through the coil, which gives us a changing direction of force and also size of force on the top of the coil. We have reversed the direction of the field because the direction of the current is reversed down here. It comes in along here, so it comes out along here, so that the force top and bottom of the coil is in the same direction. And so the coil will vibrate according to the frequency of the alternating current flowing through it.